research people to come into this area. I'm thankful for the team of IEEE student branch and the second seminar that workshop we are being hosting. And I welcome once again from student branch of IEEE CRC College of Engineering. Thank you.
Thank you, sir. Thank you very much. Now I will request Dr. Amitabh Roy Chaudhary, sir. Please take it over.
Thank you, Deepa Chaudhary, ma'am. Again, welcome to India, Professor Yellowneck. Professor Yellowneck is a successor of Professor Manpreet Thum as a director of Institute of Pulse Power and Microwave Technology, and he's also a professor of IHE at KIT. And I would like to thank Professor B.N. Basu to make it possible. I am very happy to welcome Dr. Lalit Kumar as a chairman of this webinar, today's webinar. So welcome, sir, and I request you to take the mic.
I will request all the audience to please mute their mic because it is creating disturbance for others. Just a sincere request.
Okay, sir.
Thank you.
So, Dr. Raj Chaudhary, you asked me to take over now? I think the sequence was different. Anyway, well, at the outset, I want to thank Professor Basu as an entire team for organizing this wonderful event. And it's my pleasure and honor to chair this event. I am glad to welcome Professor John Yellowneck, Director of the Institute of Pulse Power Systems and High Frequency Techniques Division at the Karlsruhe Institute of Technology, Germany. He is a foremost leader in the field of gyrotron in the whole world. And KIT has kind of a world record in the development of millimeter wave gyrotrons. So we are very fortunate that Dr. Yellowneck has agreed to deliver a talk to this community of vacuum electronic device thinkers, which Professor Basu has assembled together during the pandemic. And it's have about more than 100 members, and I'm glad that all these members have come together to the initiative of Dr. B.C. Roy College of Engineering. And on a personal note, Professor Yellowneck, you might not know, we are connected in many ways. I was with Professor Schunemann at in Hamburg Harburg for a while, about a year in '85. And he was my guide, and I was working at Volvo. And I'm proud to say that I was associated with the first gyrotron developed in Germany at 70 gigahertz, 200 kilowatt at Volvo. I also had a opportunity to work with him as a co-editor, co-guest editor of the 2018 issue of the special issue on vacuum electronic devices. And had a very good, fortunate, and cohesive relationship with your predecessor, Professor Thum, who is present here, and Dr. Hochschild, who was the founder of your center and Gyrotron there. So it's my personal pleasure and privilege to invite you, Professor Yellowneck, to this event. And I would like to say in German that ich möchte Sie herzlich willkommen zu diesem Konferenz und hoffe, dass Sie diese Seite sehr gut genießen. So I now invite Professor Yellowneck to please deliver his address or his talk on gyrotron basics and trends.
And I think, hello. Doctor, yes.
Excuse me. Before the start, I request Shukla sir to have some few words to inaugural function.
Sure.
So I would like to request Shukla sir of IPR Gandhinagar to present his inaugural address in a few words. Shukla
Okay,
sir,
sorry.
take the mic.
Sorry. I thought the sequence is changed.
Okay.
Dr. Yellowneck, I reserve my invitation to you, which will come later.
Okay. Okay, good afternoon, everyone. This is a special moment for me to deliver this inaugural address. I feel honored for that. And it's my pleasure to give a short address today on the very impressive talk for this my Dr. John Jalonak we will have in this. I wish to say actually in last 2 years it was a difficult time. Like this is a COVID pandemic, and how such difficult time can be used. We can see that how this Basuji has created a platform in this time, and it has become a best thinkers group. And this group is now expanded and it has created a very good book in national level, and now it is globally recognized. Last talk was Professor Manfred Thum, and today it is a person by Dr. John Jalonak. It will be the talk. It is a very good thing. So today at this special event of today, it's a special event of this Beth Thinkers group. This is a special talk by this Dr. John Jalonak. Actually, what I want to say in this Gyrotron, I want to say this is a gem or this is a jewel in the family of high power microwave, because this Gyrotron is basically uses the real diamond in this thing. So I want to say that this is a real ultimate in this high power Gyrotron. This is the ultimate combination of highest frequency, highest power, and highest duration. So this is something like a very most demanded high power microwave tube. So we all know the application of Gyrotron in the various fields. It is in this right from this material processing to this medical, defense, and of course the main application is the fusion research. In the fusion, it is most demanded source. Gyrotron-based ECRS system is not only responsible for startup, it is responsible for this plasma control also, like suppression of NTM by this ECCD. And in the most of the machines, in the superconducting machines, this Gyrotron-based system, ECRS system, is a mandatory system. Because without this Gyrotron system, we cannot produce the plasma. So this is an electrolyte machine. It has several megawatt of power will be used for this type of things. And IPR has a very long history of Gyrotrons, I would like to say. Because we commissioned first Gyrotron in 2000. And in the 28 gigahertz Gyrotron, 200 kilowatt Gyrotron was commissioned on Tokamak Aditya. And we carried out several experiments on this breakdown and experiments on this Aditya Tokamak. And the Gyrotron was from the CPI and transmission line from Russia, and this launcher was designed by IPR. Later, 82.6 gigahertz Gyrotron was commissioned at IPR to carry out experiment on the SST1. The 82.6 gigahertz Gyrotron, we can say it is a first Gyrotron. I would like to say this Gyrotron is first Gyrotron which was tested for 1,000-second operation. Because before in the around 2008, I don't think that any Gyrotron was tested for 1,000-second operation. We tested it here, and it was we can feel that how difficult it was at testing. We have to maintain all the interlocks, all the parameters, and we could see that there are several heatings at the several like transmission line components, Gyrotron components, and this 25-degree temperature becomes 45-degree temperature of this dummy load. Well, and although it was only 200 kilowatt of power, but we were tested for the 1,000 second, it was enormous. We got this calorimetric measurements and a lot of the things, and we could feel that, okay, this is the power for 1,000 second. Later in 2013, we commissioned another Gyrotron, that is 42 gigahertz, 500 kilowatt, 500 millisecond. And this system is basically most successful system in this SST1, and this is the responsible system for this for the startup of this tokamak, SST1 tokamak. And this the system 2013, this is working fine. This Gyrotron we procured from this Gyrotron transit line we procured from this Jaycom Russia. And this system we later connected to another big transmission line, be connected from SST1 to Aditya Tokamak. And we carried out several experiments, and this is still working system. What recently we have done, we have replaced the Gyrotron tube, because this Gyrotron is very old, almost 8 years it has completed its filament hours. So we replaced the Gyrotron. And in this future plan of our ECRH, we are again upgrading this 82.6 gigahertz Gyrotron from 200 kilowatt to 400 kilowatt system, and it will be used in the SST1. I will little comment about one more activity at IPR on this Gyrotron. This is ITER India Gyrotron. This is a 170 gigahertz Gyrotron, which was basically which is procured from this JICOM. This we have received at IPR, and soon we are planning to commission this Gyrotron at IPR. So we are doing all these preparations, and almost this test site is ready for this one. And hope in this in the next month we will be able to test this 170 gigahertz Gyrotron at ITER India lab. So we have a long journey of Gyrotron, and today's talk, it will be certainly very much beneficial for all of us, that we will have a good discussion on this, and this will be useful in the terms that this world is waiting for more and more Gyrotrons. And we heard about in 2016 onward, we have hosted, discussed with Professor John Jalonak in this previous year, 2016 at TC19 at IPR. And we met at Soft Symposium also probably, and some other distance. So we know that in several talks I have listened that in today's world, we are talking for a multi-frequency Gyrotron. And you have talked about this depending on this experimental need, because people are using, maybe go for this fusion machines, maybe more than 5 Tesla operation. So we have heard about that. We are working about this more than 200 gigahertz Gyrotron, and for more than 1 megawatt and 200 megawatt, 1 megawatt and 2 megawatt of Gyrotron. So this world is waiting for 170 gigahertz Gyrotron from this KIT. And I have information that KIT has a very good news results on this this field. So I would congratulate Professor John Jalonak for these achievements, recent achievement for the Gyrotron. So with these words, I am concluding my address, and I congratulate my Beth Thinker group to organize Dr. John Jalonak talk. So I thank you for that. And this one, I conclude. Thank you very much.
Thank you, Dr. Shukla, sir, for a great inaugural address. Is there any Professor Karthikeyan, sir? Sorry, Karthikeyan sir is not here, but Karthikeyan sir has a very good relation with KIT through Professor Manfred Thum and Professor Dr. John Jalonak. And he is not present to present his inaugural function. Now, I would like to request our chairman, sir, Dr. Lalit Kumar, sir, to take the mic and start the lecture of Professor Dr. Jalonak. Dr. Lalit Kumar, sir.
Okay, thank you, Dr. Chaudhary. So, I think Professor Karthikeyan has got, he's currently the Dean of Student Welfare and so on, and examination time is there in the university. So, I recently had a talk with him.
Okay, sir. Okay,
sir. Most likely he's suddenly caught into something.
Okay.
Otherwise, he wouldn't have liked to miss such an important event.
Exactly, sir. Exactly.
So anyway, I hope he will join later. Okay. So Dr. Jalonak, we invite you now for your talk without taking much time, and look forward to it the best possible. Please.
Thank you very much. Thank you to all of you. Special thanks, of course, to Professor Basu for inviting me and for organizing this nice event. Of course, also very much thanks to you, Professor Kumar and Professor Shukla, and of course, Dr. Chaudhuri. I can say now, earlier we said just Amitabh, we were very happy. You made a very nice PhD degree, of course, at KIT. So as said, the contacts to India, of course, are very long-term. And here I have to thank, of course, as you mentioned it, my PhD advisor, Professor Schünemann, and of course, Professor Tom, who initiated these contacts to India very strongly a long time ago. And of course, we are well aware that, of course, India, and Professor Shukla mentioned it so nicely, is also doing quite a lot of things in experiments. And with Professor Karthikeyan, also a strong theoretical approach with a lot of papers in IEEE journals and so on the things. So I know that you are very familiar, most of you, and very famous also in Gyrotron. So it's a big pleasure for me to present here, of course. And I know you are taking also a lot of effort for ITER to build a system in India and also to deliver to ITER. So therefore, I will start my presentation with big thanks, and I hope I can present you some new things. We will go through nice things. Of course, I will start with some basic introduction. So with this, I will share my my screen.
Before start, I would like to one more request. Please turn off all the mics and videos. Please turn off.
Yes, thank you very much. It will help maybe. Please let me know if you feel problems in looking at the presentation or so. I wish that you can see it. Now, can you see my, now it seems to start.
Yes, it is visible, sir.
Okay, thank you. So
Yes,
then we can
yes.
start with the presentation. So again, I'm very much honored. I was asked to give a presentation on Gyrotron basics and trends. Professor Shukla did already tell a bit about the gyrotrons and said it is a gem in the world of vacuum electronics, and so it is. And that is why I'm so fascinated, having been in industry with completely different things working, but at my final end, coming back to the Gyrotron, because it's a gem in research and a gem in what we can achieve also for humankind, considering that we need renewable energies and new energies on this and new technologies for that to for our children and for our grandchildren then and this and then for the future. Here you see also in the very first slide that this is, of course, not a work only of KIT. That would be by far wrong to say. Of course, in Europe, in the Gyrotron research, we are working close together. Also, we were, of course, working close together with our colleagues. Unfortunately, what happens at the moment, but we had close contact to Russia, close contact to, of course, Ukraine, close contact to India, to China, to US, of course. And there we are very proud of, and also, of course, to India and these contacts. And here, when we develop the gyrotrons, we are very closely working together in Europe, particularly with EPFL, which is in Lausanne in Switzerland, of course, also in Athens in Greece, also with Siena in Italy and Politecnico di Torino, also there, and IPP in Garching and in Greifswald in Germany. You know that in Greifswald is a big stellarator W7X on this. And of course, it's coordinated, the things are coordinated in Europe when we, of course, in for the ITER and fusion for energy and for the all the research what we are doing go towards the European demonstration fusion power plant. This is coordinated via the European fusion program, so Horizon 2020 and Horizon Europe, and this is called here Eurofusion as for the work what we're doing on the research. So what you see here, we are moving through a lot of topics, of course, giving some introduction to the persons who are maybe not so much in this field. And I apologize for all, especially, of course, Professor Kumar, Shukla, Basu, Chuduri, you know a lot of this, and hopefully it will not become boring for you when I have some Gyrotron basics later. Going into the megawatt class developments of Wendelstein 7X, of course, we are continuously working with Wendelstein 7X and improving there and going forward. For the EU ITER Gyrotron, you heard we are now selected as some Gyrotrons for ITER. I can say not we, but with a European industrial partner. Of course, you know, every continent, so to say, has its industrial partner. So Europe has Thales, and Russia has Chicom, and US has CPI. So we are working very much in Europe with Thales together since 20 years already in minimum. We have close collaboration on this. And then we will go forward for the, of course, the 2 megawatt class coaxial cavity technology for demo. I will introduce a bit to the world first E-cross-B drift multi-stage depressed collector technology. Yes, we have pushed through it, and you know also our colleagues in Russia have started on working on this, so following us more or less. So, and then we have the towards we go also smart control of gyrotrons, because first you have something made in the physics. As always, you start today with digital controls, smart controls, and going forward, advanced things to get more out of the gyrotrons. And finally, we go to the test stand for what we call Fulgor, so a fusion long pulse gyrotron lab in Karlsruhe, which is in total a 10 megawatt CW gyrotron test stand. So starting with the introduction, as Professor Shukla said, and as is this electron cyclotron heating is one of the major heating systems. So what I learned also then from my predecessor, from Professor Tum and others, and that of course in earlier days NBI, ion cyclotron heating, lower hybrid was considered as the major heating systems. And you see the three heating systems here: ion cyclotron heating, electron cyclotron heating, and neutral beam heating are still in this ITER. So a nice collaboration on this. And everyone will see what comes for the future. But it shows that the electron cyclotron heating, and you see how compact it is going to the tokamak, is one of the systems which is considered for the future. You see also in the upgrades. So the first is the installation, and the second is, of course, the next what is coming in future on this. And this is, you see, 20 megawatt now, and maybe additional 20 megawatt electron cyclotron heating for the future. As such, for the electron cyclotron heating and the ion cyclotron heating, both as the RF heating systems, you see here the ion cyclotron heating at 40 to 55 megahertz, really in the low RF region, what we will say, and the electron cyclotron heating at 170 gigahertz, fitting to the magnetic field of the tokamak system. When we look on the ITER, of course, for the ITER, we have to say, if we look on the gyrotrons, we see here installed is 24 megawatts. That means 24 times 1 megawatt gyrotrons, which are going to lines and which are then going through so-called launchers, so upper port launchers and central port launchers, which are then going out to the equatorial port, and you see here the launcher and the top launcher to the tokamak into this. Additionally, we have a certain, of course, long transmission lines. This is a nice thing for the gyrotrons and for the high frequency operations that we can use quasi-optical systems, or we can use transmission lines to overcome even large distances from the gyrotrons to the tokamak, and are very flexible in locating these gyrotrons. So if we compare it, of course, with the Wendelstein 7X, so the Stellarator in Greifswald, then we see here also the gyrotrons, and you see here one of the gyrotrons installed, or originally installed in the Greifswald system, so easy heating system in the magnet. You see we have there 10 gyrotrons installed, which are in 2 rows of 5 gyrotrons, and they're using really quasi-optical transmission lines. You see this quasi-optical lines. Each of the lines is transferring 1 megawatt of the gyrotrons, and this is combined then later in the plasma, is going through air. So this is a very nice and simple system with moderate loss and very good possibilities to transport the RF. So when we look now in total on this, of course, for us in Europe, I named it already, the Stellarator Greifswald, Wendelstein 7X, and this was actually the start for us in the beginning of the 2000s, end of the 90s of the last century. And then the development of this finishing in 2015 with the first installation was a 10 megawatt EC system of Greifswald with a frequency of 140 gigahertz operating at the second harmonic of the plasma in this. So this that was the 140 gigahertz. With this, of course, the next step where we were working on is, of course, the 170 gigahertz 1 megawatt system gyrotrons, which is then giving the 24 megawatt, out of which it also India will deliver 2 gyrotrons or is expected to deliver to ITER, but Europe 6 gyrotrons, Russia's 8, and Japan 8 gyrotrons on this in the first installation. And of course, what is for us the major research and development is not even ITER. It is already what comes after ITER. What is the advances for ITER? What is the advances for W7X? And when we look now in the European demonstration fusion power plant, which is expected between 2040 or 2050 to be built, then we see that we have their multi-frequency operation, as it was nicely named by Professor Chukla. The major is 170 and 204 gigahertz. You see already above 204 gigahertz, but with the possibilities also to operate at 240, but also low down to 136 gigahertz on this. In this, and the total installed power shall be between 70 and 150 megawatts. So at the moment, it's considered to have around 30 megawatt central heating and 70 megawatt even plasma control. So we have minimum between 70 and 100 megawatt of installed power there on this. As said, multi-purpose operations, that means at multi-frequencies. Frequency steering into the plasma with frequency steering, that means in steps of 2 to 3 gigahertz to go into the plasma. Operation at long pulses, minimum 2 hours on this, and sufficiently high plug-in efficiency. So that means at the moment it's planned 50% minimum, but originally above 60% efficiency for the gyrotrons as such. So these are the targets we are targeting for and going forward in our designs. Even there, it is the question, of course, what is if we go for higher EC power, higher EC efficiencies, higher EC frequencies? Also, another next step is, as I said before, is intelligent power and frequency control for the gyrotrons, for power combining, for power stabilization, for diagnostics, so that we have, for example, Thomson scattering diagnostics, which we can make. So on this, so this is where we look for, and of course, then also derivatives of demo, maybe also smaller tokamaks, even going for higher magnetic fields, and that means also higher frequencies, for example. If you look for the fundamentals on the vacuum tubes, of course, everyone knows the standard magnetron. So for the people who are not so aware of the gyrotron itself and what is this size and what is this, then we know, of course, the normal magnetron, the normal klystron, the normal traveling wave tubes on this, which are in relatively compact size on this, and of course in relative moderate frequencies. So below 30 gigahertz most, or at 30 gigahertz most today still on this. A lot of people know going to higher output power, of course, remembering then the klystrons, which are made for accelerators, for example, in this, and we see it here mostly operating between 0.3 and 3 gigahertz, and this was a classical for the classical accelerators going to expand if we go for the advancing in CERN and so on this. But for all of them it counts. The one counts, the size of the tube depends on the output power you have, because you have a limited efficiency and you have of course high losses, and this losses means thermal heat of the tube. And as said, when we go from kilowatt level, which we can have in the really compact size, going to megawatt level, it means with a limited heating of the material, we need to get larger. This is the one, and therefore you see the klystron here with a human at side, a researcher there, in the size of 3 meters, whereas a magnetron is maybe 10 by 10 centimeters or something like that. But we also see that we are limited in the frequencies, because for all conventional vacuum tubes, it counts power multiplied with frequency square is equal to a constant. This is also valid for solid state devices, actually, also on the material parameters of solid state devices. So this is for all classical sources and oscillators on this. That means if we increase the frequency, the power availability you have from the tube goes down with classical structures. And this, of course, you see if you go to a presentation which is already quite old, but from Dr. Levush from the NRL on this, what he showed on this, and you see on the left side on the y-axis, you see this famous law, power multiplied with frequency square, and on the horizontal line, the development of the gyrotrons in the years. And you see that the achievable constant, if you have a certain development status achieved, you will never overcome. You will go to a limit. So if you want to go higher and higher, you have to do something different. And what you see here, more or less, you have only the possibilities with non-classical tubes. That means somehow the gyrotron, yes, the gyrotron at a certain time saturates too, but also with the free electron laser, also there you will find limits at a certain point. But compared to the classical tubes, you can go to much higher levels on this. And this, of course, is the reason for the gyrotron as it works with the principle using the Bremsstrahlung as principle and interaction method between the electron beam and the microwave on this, and not the classical Cherenkov radiation or transition radiation used in klystrons or TWTs. Because this both here marked in red, they have the classical resonance structures in the order of the wavelengths or even smaller of the wavelengths, sometimes than in the electron beam distance to the structures, very much smaller than the wavelengths as such. So that means if we consider that we go above 30 gigahertz and then the wavelength is a centimeter, or we go to 300 gigahertz, where the wavelength is a millimeter, that you are going to structures which are becoming very, very small. So that means, yes, we have no other choice today, but we have also the choice. Say we have not a known other choice, but we have the choice to go to so-called gyrotrons or free electron lasers on this, but we go here for the gyrotrons on this. And because of the coherent radiation by Bremsstrahlung due to electrons with relativistic kinetic energy encircling a strong magnetic field in a simple overmoded waveguide. This is the key and the success of the gyrotron as such. Now looking into this, knowing that why we are going there, and then the question is how it looks in general. And here I want to show you something at the beginning, what is made, a video made in our lab. And this video shows first our Dr. Gerd Gantenbein, of course, Professor Shukla and Professor Kumar and others will remember him, He is the department manager, and he managed actually also the Gyrotron activities on our lab. He's also the project manager for the new Fulgor test stand and coordinates the ITER activities. So he's very much to honor to the work what we are doing, and he is of course welcome to show you, so via this video, the ITER Gyrotron what we have, that you get a very first impression. As I recognize you will not listen to the video, therefore I will a bit make the speaker for him, yeah, because he talks in the video and you will only see it probably. So, but let's see how it works. So you see, he is a gyrotron, and you see on top the collector. So in this, we are in the gyrotron test stand, and you have seen the length of the gyrotron is around 3 meters. The gyrotron is in the magnet located. This is a 6.7 Tesla Oxford instrument magnet, which is very flexible and has a borehole radius from diameter from 270 millimeter. You see now in the lower end, you see the magnetron, the inverse magnetron gun located, and you see on top a quasi-optical output system, and with a diamond disc where the gyrotron, the RF is coupled out of the gyrotron, and on top you see the collector system here on this.
The electron beam, and which increases the efficiency of the device. What you see here is several coils.
Another thing, what you see there is, of course, you see the big pipes are water cooling pipes, and you see additionally here coils, which are coils which shall move the electron beam and vary the electron beams cyclically during the operation in the collector, so that the collector maximum thermal load of the collector is going down. So with this, you have seen the size of the gyrotron. This is a 1 megawatt gyrotron, 170 gigahertz in a magnet operating of 6.7 Tesla. As we know, the famous relation via the Lorentz force equation, 28 times the magnetic field is delivering you or close to the operation here. Of course, we have here to consider the relativistic mass of the electrons, because the electrons get a very high energy here for the working principle, and then we have a frequency around 1.1 times the 28 times the magnetic field for the frequency of the gyrotrons.
We are here at the
Yeah, now looking on this gyrotron and showing a bit through this gyrotron, you see that the components, so it's quite simple made. So you have more or less a magnet, the outer 10 Tesla magnet, and as such, I will go to the laser point, and you see the magnet here, where the gyrotron is located in. So the magnet has really this borehole. The borehole size, as said, typically between 220 and 260 millimeter, for example. And this, if you have multi-megawatt class gyrotrons on this, and there's the vacuum, of course, the vacuum sealing on the outside. And as such, you have on the bottom, you have the cathode for the electron beam generation, and as such, with the cathode here itself, of course, we have the issue that this is not an electron beam which is going out like a classical traveling wave tube with a classical Pierce gun. Here you see this orange is the emitter, and the emitter as such has is a thermal emitter in as such, and this emitting the electrons in axial direction of the tube, but also has the electrons become through this emitter ring a transverse velocity. So we have an axial velocity and a transverse velocity, and both together, of course, transverse velocity divided by the axial velocity gives us the alpha on this, so on the ratio between the both velocities. The interaction later in the gyrotron goes only via the transverse velocity of the electrons, and you see the electrons are encircling on helical movements through the magnetic field. So the blue is the magnetic field line, and you see, as it shall show here, the magnetic field is getting higher. It is more condensed, and we get with this we get also transformation of the axial velocity to the transverse velocity for the electrons according to the Bush theorem in the so-called beam tunnel. If we go to the next, after the cathode, then we find the interaction zone or the resonator of the gyrotron. And if you remember this on a traveling wave tube, you have a quite complex structure to achieve the traveling wave, the electromagnetic field as a traveling wave. You know the klystrons or others where you have an input cavity, an output cavity, and you have acceleration cavities in between, buncher cavities that you don't have here. The principle on this is quite simple when we are going here. So it's shown also here, the interaction region, because it is not more, as you can even see here, a little bit of an inhomogeneous waveguide. You have more or less in so-called down taper. So this is a first entrance of the cavity. Then you have a straight structure, and you have an up taper with also a small angle degree of 1 to 3 degrees, and that's all what you have for the interaction cavity. In the interaction cavity, the magnetic field, so therefore it's in the center of the magnet, the magnetic field is highest, so to that field what you want. That means 28 times magnetic field divided by the relativistic factor, typically 1.1 in this area, what we have, gives you the resonance frequency for the electrons, which interacts then with transverse electric field mode on this. Of course, transverse mode, because we say that the transverse, so the transverse velocity of the electrons are interacting, and of course the electron beam interacts with the electric field on this, and therefore we are interacting with the transverse electric mode. Here it is a mode which is, this is for W7X, for example, TE288 mode. That means very high compared to the fundamental modes often used for the klystrons or for traveling wave tubes or others in this. Yes, why? Because we have structures which are large compared to the wavelengths of the electromagnetic field. So considering a wavelength maybe at 150 gigas of 2 millimeter, we might here have a radius of 2 centimeters to 4 centimeters on this for the cavities. Then you can imagine what number of modes you have which can excite here. The selection of the mode you of course do in two ways on as such. So one is, of course, you look that you have a certain axial profile, which I show later on this. So that means you choose the mode that it has, that it fits to a certain resonator. Also vice versa, I have to say, of course, you design the resonator in a way that you get the profile. And another thing is you want to have a you design the mode in a way that it is close to cut off to the straight section on as such, yeah, that the phase velocity is getting to 0 on the electromagnetic wave, so that you have no dispersion on this, not dispersion here, sorry, this, so that is very close, of course, the resonant frequency to the cutoff frequency of your electromagnetic wave. And as such, you have, of course, a Q factor on this, which is around then of 1000 on this. When we look on the interaction mechanism, and I'm not going too much into the interaction mechanism here. The first is what I said. Of course, you choose a certain axial profile as such, of course, For the electrons in the first stage, you make that the electron bunch in the decelerating area of the electromagnetic field, and you can go here and look through this diagrams and this. So in this, most of the electrons shall bunch in a certain area, and then in the highest field region for the transverse field, there's highest in the center of the cavity, most of the field shall be given to the, or most of the kinetic energy of the electron shall be given to the field as such. Of course, the working principle set to here, if you look at this, if you are new on this, means is that the electrons have a relativistic velocity. That means if they are in an accelerating field area of the in the cavity, then of course, when they are accelerated, their mass is increasing. So if their relativistic mass is increasing, then their cyclotron frequency, according to the Lorentz force, is decreasing. And for that, you get the bunching process if you look at this. And this is nice if you just follow here the diagram and look for yourself to see how it moves through the cavity. If we go to the next, then of course we have a quasi-optical output system. In the very old gyrotrons, as of course Professor Kumar said something around in the 80s, but also in the beginning of the 90s, and I can even remember when I did my theoretical PhD with Professor Schünemann, we were considering axial output. That means an axial output means that the RF would be guided through whole the gyrotron, and the output is axial. So what would that mean? That means that the collector must have a certain maximum diameter, because otherwise you get a very overmoded structure. Additionally, you have to guide the generated microwave field through this collector, through this waveguide, and which is at the same time the collector. And with this, it means that would be one major limitation for gyrotrons in megawatt class area. So this is actually one of the limitations. The second, of course, the electron beam, what you can generate. And the third is, of course, how much power you can get out of the system. But as such, here you see the quasi-optical system together with the launcher system, and this developed by our colleagues in Russia, of course. In this is at first the quasi-optical system, which consists of a launcher, so-called launcher system, or waveguide antenna, you can call it, and quasi-optical mirrors, 3 or 4 quasi-optical mirrors, and then a dielectric window, a diamond disc. Then you can see this basic principle of the system and how you outcouple it. Here you see in the launcher what we have. In the launcher, we convert the rotating mode. So we take a or counter-rotating TE mode, which is generated by the electron beam, is then converted to a linear polarized TEM mode, which is then going out as a Gaussian mode through this microwave window. Showing into this is a real system as we build it for our gyrotrons. Of course, we are not using any more phase correcting mirrors. We have seen that phase correcting mirrors is maybe not the optimum on this. Therefore, our launcher system is improved as such to convert the TE-MP, so TE-28.8 mode to a Gaussian mode, which radiates through the launchers, through the mirrors, and goes out as a Gaussian beam, is optimized. So the very final, which one can show on this, is regarding the window, and this as this second or third major improvement to come to megawatt class gyrotrons was where my predecessor, Professor Tum, was actually very much involved in, of course, KIT was very much involved together with German companies and other companies, for example, Diamond Materials as such to develop large size diamond discs with CVD manufacturing technologies. You see here the companies Diamond Materials, it is Fraunhofer in Freiburg, and Element 6, well-known De Beers, which are building it. Because diamond is the only material which has sufficient low losses. It shows here tangent delta 2 powered with 10⁻⁵, and an epsilon r, which is of course also reasonable, is 5.67. And it has a very high thermal conductivity here on this, which is sufficient to spread the losses in the window to the outer cooling of the frame of the diamond disc. As last, we have the collector, and you have seen the collector is, I would say, half of the gyrotron in size. Why? Because of course we generate or say we convert the kinetic energy of the electrons, and for this only around 30 to 40% maximum, we convert it to microwave, which is coupled out of the gyrotron. The remaining would go to the collector. And for this, you need two things here. A collector which is large enough to can even convert the thermal heat of 1 megawatt. If you have a 1 megawatt gyrotron, you need 2 to 3 megawatt into DC input power. So it need to be strong enough to withstand this 1 megawatt, which is coming from the spent electron beam. And additionally, you have something that you can reverse the voltage. You see it here and plotted here, so that the electrons are already decelerated when they go to the collector, the spent beam. And with this together, so if we count the 30 to 40% electron efficiency during in the interaction cavity, together with around 50% on efficiency, which you can get for a certain recuperation voltage, then you come to a total around 50% efficiency for a gyrotron. So this is a third which you need to go to megawatt class gyrotrons. Now we come to having now done a very short, and I apologize, very short, the gyrotron basics, of course, on this. So it's even very difficult to explain when to do it so condensed. We are coming to that what we are doing actually with our gyrotrons. And the one is, of course, the W7X, as I said. The second is, of course, the ITER, and the third is the European demo. As such, we are going to our presentation as such. First, I name it megawatt class gyrotrons for Wendelstein 7X. Yes, earlier I would have said maybe a 1 megawatt gyrotron for W7X, but this is already old. So we are going for 1.5 megawatt and having interest to going to a 2 megawatt gyrotron for W7X, as we see that W7X has also the need for higher power densities in the plasma with the same number of gyrotron ports. Going first in the 1 megawatt gyrotron, and a lot of you will know this gyrotron. It's a 1 megawatt gyrotron. Actually, in long pulse, it is set minimum 920 kilowatt, and as such, in 1,800 seconds. Yes, it is tested and operated all gyrotrons to go in this pulse length as such, operating at 140 gigahertz. They were never made for something operation for 105 gigahertz, but you can find modes where you have maybe half a megawatt or so operating on this. And the classical on this, we have seen it before, and it's the Magnetron Injection Gun. This is a so-called diode type electron optical system, which we have here. So that means you have only the cathode and anode voltage. You have not a third triode voltage, where you can reduce the electron beam or change electron beam parameters as such. You would need another triode voltage supply on this, and this we prevented. In some areas today, you would say go for a triode system, but at that time we had a diode system installed. A nominal beam current of 40 to 50 amps with a voltage around 80 kilovolt. As such, you can calculate what is the total DC power going in and what is the power converter, which is more or less a gyrotron, is converting into the 1 megawatt output power. The cavity magnetic field is 5.6 Tesla to achieve the 140 gigahertz, and the quasi-optical mode converter, here it is a standard Denisov converter, is around 97%, and we have the diamond disc, of course, on this, and we have a voltage depression body voltage around a maximum 30 kilovolt. We are normally going a bit lower on this. When we look on this, we see that the W7X, and here I put an empty cases. Yes, we are discussing with several others, which I have not shown here, on relatives of the W7X gyrotron, very concrete and running is a dual frequency gyrotron for TCV and EPFL. For the medium sized tokamaks, there are 126 and 84 gigahertz 2-second gyrotron. Yes, we are discussing with West, with others, D3D, with others on this to go for gyrotron relatives on this. But we are, as said, want also to go to the 1.5 megawatt gyrotron on as such. And this is very concrete looking here. So what we did, as such, we said the most difficult for a gyrotron. So what you have to do at first is, if you make the first design, make it large enough and make it in a way enough that your cooling system is proper enough, for the, especially for the cavity cooling, gun cooling, diamond disc cooling, collector cooling, that you can advance for later in the same frame. And luckily, the W7X gyrotron at first are a bit larger than others when you look at other gyrotrons and this. But they have the big advance, we don't need to rebuild all the mechanics. So what we did is that we only very slightly increased the radius of the cavity by less of a millimeter and changed a bit the length and the optimum of this, going from a TE28.8 mode to a so-called TE28.10 mode. Additionally, we optimized a bit that we can go from current from 40 amps to 55 amps and using similar accelerating voltages for the electrons. As such, we are getting something where we are then having 1.5 megawatt in operation for this. Of course, also with some minor improvements on this, with improved cavity cooling, improved voltage feed-throughs, and adjustable mirrors to get more accurate in the output on this, gives the new gyrotron. Here you see something, now we fell hook. This is looking much smaller than before this gyrotron on the picture. This is what we are building in KIT, not always, but more oftenly, that we said before we go for an industrial gyrotron built by an industrial supplier, we build by ourselves a so-called short pulse gyrotron. Short pulses is in our wording a gyrotron operating in millisecond pulses. So millisecond pulses, and then of course the duty length is the duty cycle is very small on this. So when you repeat the pulses, allows you to make the collector much smaller, allows you to remove certain coolings, for example, cavity cooling, or make a very simple cooling on this. And also it means you can just operate without special conditioning of the tube. Yeah, the vacuum keeps quite good even when you make several pulses on this. So that means you don't need to brace the gyrotron. You can screw this and fix it with this much simpler connections, the different interfaces of the gyrotron. With this, yes, we have done the short pulse gyrotron from the physics design exactly the same as the CW gyrotron. I can say the CW gyrotron will come, is ready, is already manufactured, and is coming in latest three or 4 weeks, say, if it is delayed, otherwise earlier. And so it's a short pulse gyrotron, we made output powers above 1.5 megawatt even. So that we can here say, of course, we have different operations done from 1 megawatt to 1.5 megawatt to find what we can get with this gyrotron out of this. And you see here the efficiency is significantly improved with the new designs and what we learned over the years to improve the efficiency in the gyrotron with the improved coolings, cavity coolings also on this, and then going to the output power, to the higher output power. As said, this gyrotron will be end of April latest in our test stand and installed in this. So far, we are installing in the Fulgor, in our new test, and I will show the 1.5 megawatt short pulse gyrotron. Going for that, then we can say, of course, you know, we did in the very early an ITER 2 megawatt gyrotron, which in 2012, unfortunately, had a simple failure. And all the people said, kill it, go for 1 megawatt. Therefore, we said, yes, we make a derivative of the W7X, and it was always said you have only 1 year time to improve. So we could not do what we like to do that, to make a fundamental redesign on the thing. So we made more or less an upgrade, but is also working. It's an ITER 1 megawatt, 3,600 seconds, 170 gigahertz tube, and the same tube will also go for the diverter test tokamak to Italy on this. And this will also, of course, a base if we will be asked for an upgrade of the gyrotrons. This gyrotron goes to an even higher operating mode, the TE32-9 gyrotron with, of course, higher magnetic field as we have 170 gigahertz operating frequency. But you see here very similar, so this is the original design, very similar accelerating voltages, depression voltage, and so forth. You see very similar to the W7X, and here's the original gyrotron installed in the KIT test system as such. When we look on the upgrades compared to the W7X, we can say we have an optimization of different components done. Of course, we have improved the Magnetron Injection Gun. You know, Dr. Pagonakis has done a lot of fundamental papers on how to improve and how to parameterize the design of electron guns so that we have an optimized Magnetron Injection Gun for the ITER tube with very low transverse velocity spread as such and an optimized operation. We have, of course, learned a lot about launchers. You know that Jumbo Chin in our team was moving forward from classical Denisov type launchers to mirror line and hybrid type launchers, which make it much more compact and with very high conversion efficiencies and very high Gaussian mode content above 98% here. Low stray losses, which is important to have low losses in the mirror box. As such, you see here what is for the ITER gyrotron done at that time. This was for the original design. Of course, over the years, we faced some issues with that, of course, and therefore now for the final design, we refined the RF design. We have a better cavity cooling. We have an improved increased margin on the depressed collector high voltage capabilities. And we have an improvement of other subcomponents, even in the alignment of the subcomponents, so that we have done an upgraded gyrotron. And you see here there's a paper published, which is quite recently, it's just now, say, on the market where you can read it, about the experimental testing of the European gyrotron in the KIT test stand. This is in the Electron Device Letters of April of this year, published on this. When we look at this on the verification at short pulses, we find that we found very smooth operation, a body voltage stand of up to 40 kilovolts. So that we can go for, this is something that we can go for high depression voltages. And we generated output power. Here you see up to 1.2 megawatt, and interaction efficiency is close to 30% with this tube. Going to long pulse operation, we have to say so far, and that was the reason building a new test stand. So far, everything was running in a very old test stand. Professor Kumar mentioned before that Dr. Hochschild was the first one, and actually in 1983, this test stand was built up for 500 kilowatt max output power. So we improved it, and now we could go with this only to a certain limited number of seconds on this, but so was going to 40-second pulse length, which is of course then in the steady state regime already, with 1.044 kilowatt in 38% efficiency in the limited depression voltage which we use there for this operation. And before we had to pack it, and then it was going to Lausanne for further testing the tube. So you see, it has shown there the capability of this tube. Having done this, of course, we are now going to that what is our most in research. It is, of course, the demo in the Eurofusion research and in the multi-frequency tube, multi-purpose tube, operation at long pulses and sufficiently high plug-in efficiencies. What is the problem on this is, of course, a typical mode spectrum in a highly overmoded cavity of a gyrotron. If we are talking here about several thousand modes which are possibly to be excited by the electron beam, we get a very, very dense mode spectrum. Here, even for the moderate TE288 gyrotron, 140 gigahertz, increasing the frequency makes the problem higher and higher. And you see, you have to do something. And therefore, KIT decided before a long time, also saying that the original design of coaxial gyrotrons also relates also to some investigation also in Russia and others in much earlier years on this, but then not continued on this. So we said, move to a coaxial cavity gyrotron, introduce maybe some corrugation in this here for the inner contour of the insert, and move maybe later also to some other operations. But now what we say here for the demo on as such on this, you see it here that we have here a different insert in the cavity region and in the beam tunnel region than we have on a classical W7X gyrotron. Here left the classical gyrotron, right the demo gyrotron, which is more or less relates to the old ITER 2 megawatt gyrotron as such, which we move forward and advance further on this. So this 2 megawatt gyrotron is a TE3419 mode coaxial cavity, which you can see here. With this, you find much improved mode selectivity and large output powers at even higher frequencies where you can go for. You have also not the problem for the that you have for the space charge effect of the electron beam or such. This is all much more moderate if you go for the coaxial gyrotron. Of course, where we are always asked for what is with the thermal loading of the manufacturer of the insert, what is the investigation of vibrations and misalignments due to a cooling, because you need to cool the inner conductor on this. Here, what you have on this. This was questions which we did here also then with Dr. Kalaria. So Pat Kalaria is not today with us. He's in industry and advancing very well in other areas, not in gyrotron anymore, unfortunately. And he did quite a lot of investigations as such, also on the insert cooling. And you see here what he did in frame of his PhD and shortly after on this, when he had an engineering grant on this, that we looked for the 2 megawatt gyrotron, and the max insert loading is 0.12 kilowatt per square centimeter. The max water temperature is very moderate, And as such, we can show that the insert is not at all a problem for operation. Also, what Pat Kalaria did is that he investigated in advance even with laser measurement systems. What is the moving of an insert when we operate in cooling? And here, interestingly, he found out if you make the water flow in the right direction, and this that the inlet comes from the outside, the outlet goes in the inside of the launcher, then you have a very smooth operation of this insert, because you don't get vibration caused by the tip of the insert. So that means the coaxial gyrotron is capable to operate in this principally. Now the question is what we have in the RF performance and going to longer pulses. And as such, we of course operated the tube very reliably. We can say the operation is much more smooth even than the hollow cavity gyrotrons that we see, even when operating at 2 megawatts. So we go in 2-3 days, we go to a 2 megawatt operation, even having dismantled and done something new on the gyrotrons. This is not always the case for standard hollow cavity gyrotrons. We see here 2.2 megawatt at 1 millisecond, which is easily and very often repeated in these things. Now it was said, go to longer pulses. Of course, what we would like to do is going for a CW gyrotron, but we know the cost on the European cost level of a gyrotron. This is, of course, related to the salary, not the technology or others. This is the salary of the European, French, and German technicians, and that means it's very expensive. And therefore, we build it by ourselves in our workshop on this, going to first to a 50 millisecond and then a second step to a 1 second tube, because we know then, as what I said before, the beam neutralization has been done, and the thermal should also go to a steady state on this. So in the first step to 50 milliseconds, we built in specific coolings and we installed a certain Magnetron Injection Gun. And the second step we are doing with inserting a diamond disc and a collector system. Here you can see the upgrades, what we really did on this. So in the collector phases, and this with a cooled collector on this and advanced sealing of the, as I said, not fixed mounted interfaces. So we are not brazing the interfaces. We have just screws on this. Much more easier to replace things. But of course, if the tube is heating up, the vacuum is getting worse on this. So we have first the sealings to make better. Second, you see it here in the vacuum oven, we need to condition the tube much better. And here I can report that we are building up a new big vacuum oven, a 10-meter high vacuum oven, where we can even at KIT very easily outbake also in future tubes for longer pulses on that. So this is just under finalization of the construction at KIT. And this is here is in the old oven where we have even to cut certain parts to bake out the gyrotron. When we look at the short pulse operation of the so-called longer pulse gyrotron, what we have, we found easily again the 1 megawatt to 2 megawatt operation on this. And then we were moving to longer pulses. Unfortunately, it was hindered then by COVID, so that we could not continue on this really in the lab. And then we moved again back to ITER and W7X tubes. But you see here's a 2 megawatt operation. And you see here more. You see the comparison between experiments and simulations. And you see when you look on the right-hand side, the comparison between the so-called Eurydice code made by Kostas Aframidis, and of course the Eurydice code relates to the old self-T, which is done by Stefan Kern in the 90s or beginning of the 90s already. Then you see how close the expectations are to that, what we measure already today in the improvements of these codes here on this. For 50 millisecond pulses, we were going to that and see already also a very smooth operation of the tube. as such. So that means what we want to do is, of course, making these upgrades now, and this is where we are building in, so that we build a cooled collector and a diamond disk, and both we make so late because it's very expensive for us as a lab, because we have no funding for that on this, so we have to do it by our own. And this, even when Eurofusion funds some things, but this they are not funding really on this, so therefore we are building this now and building together the tube. What we do next is, of course, that we said we need a multi-frequency tube. So having built the long pulse tube, we used part of the old short pulse tube, 2 megawatt, to build here. You see it's another short pulse tube which is capable of multi-frequency operation, which are built in a 10 Tesla magnet, which we are expecting to get hopefully soon on this. In the theory, you see, we found with slight modifications, we found already very nice operation even of a tube, which was never intended to go to 204 gigahertz. Of course, much better would be now we have, if you look in old PhD thesis of Joachim Frank, maybe I can only say to you, if you look into that, you find something, Gyrotron for future demo on this, and also in the work of Pat Kalaria in the PhD. Then, of course, we would go to a specific mode series, which is more optimized. But as we have to build from things which were developed over and evolved over years, starting up from the old 2 megawatt ITER Gyrotron. So we made that this is also capable for 204 gigahertz and even for 240 gigahertz. And you see that you can even here get 2 megawatt output power with the TE4023 mode, which is above 2 megawatt. Also with reasonable efficiencies as such. So this is what we want to operate, and you see here what has been changed for the operation at multi-frequencies as such. The quasi-optical system, the optimized beam tunnel, electron gun, and of the collector is not in, which will, of course, be added later on as such. This was more or less for the 2 megawatt gyrotrons where we are going for. What I did not show to you is, of course, that we are going also for frequency tunable gyrotrons with Brewster angle window developments, where we can shift the fast switch the RF in steps of 2 or 3 gigahertz, what we want. This I don't show to you because I want to go in the final end also in the introduction to E-cross-B drift multi-stage depressed collector technologies and the smart control of gyrotrons. Here for you, it's of course to know that if we have a velocity ratio, which is the ratio between the transverse velocity and the axial velocity of the electrons inside the cavity. So after the compression in the beam tunnel, we get here an efficiency which we can get maximum out of is between 50 and 70%, depending on the velocity ratio. When we look in the conversion which we can achieve, which we can maximum achieve, then we can go maximum to 70%, but realistically is between 25 and 50%. Where 50% is already far out. So in a design value, you would go maybe to 35, 38%. Of course, depending on whether you take realistic beam parameters in, or whether you put in an ideal case, which you can get, of course, above 40%, but it's not relevant on this. So if you take relevant parameters, you get above 30%, maybe 35%. Of this, also looking into a reasonable cooling at the walls, because of course also the efficiency depends on the quality Q of the cavity. When you do this around 30% to 35%, and you have an energy recuperation, so therefore this collector is so important. You can gain between 40 and 70%. Realistic is 50%. So between 40 and 50% is realistic. All others is not realistic if you calculate a realistic electron beam and a realistic depression voltage on that, what you apply, which you can calculate simply here. Out of the calculation, what is the interaction efficiency? So what you can have maximum out of the system, and what can you get as a recuperation efficiency, which is the efficiency where the spent energy of the energy of the spent electron beam is converted back and given back to the system. So if you do this, then you find out that, of course, the interactions, the electron efficiency is at most important, but you find also then here the recuperation efficiency on as such, where you can go to the 50%. And this you might improve if you are not able to improve more the electron efficiency, if you go for classical gyrotrons as such and this. So here it was that we said for the today ITER, we want to have an efficiency around 50%. But for demo, we want to have an efficiency which is actually above 60%. And that, as said before, this you can only achieve by increasing the collector efficiency. What are you doing typically for traveling wave tubes is multi-stage depressed collectors. Yes, multi-stage depressed collectors, you will say, is standard in this. But if you have now an electron beam, an electron beam which is which has a transverse and axial velocity and is not a pencil beam anymore. Secondly, you have a magnetic field which is much higher than for a traveling wave tube. And thirdly, you will see later that the spent beam, so the spread in the energy in the spent beam is much larger than you have for a traveling wave tube. You will believe me that people said before multi-stage depressed collectors for gyrotrons are not feasible at all. I will show you it is feasible, and we are building such a collector in this. And you see here also, when you look on the right-hand side, you find also here, again, on the x-axis, the electron efficiency, on the y-axis, the collector efficiency, which was before the recuperation efficiency, and here's the electron efficiency. And then you can find out at 34%, you need above 70%, 74% of collector efficiency, which you can only achieve with multi-stage depressed collector. Single-stage depressed collector has around 50%. So what does it mean? If we look on the kinetic energy of the electrons, then we find that the electrons at the beginning have all the same kinetic energy. Here we assume 90 kilovolts, so 90 kilo electron volt on this. So when we now go into the or out through the cavity, and after the cavity you see the big spread in the spent electron beams. Yeah, so most of the electrons have, of course, a kinetic energy lower than the original one. Some are larger, but you see this big spread. So if we are only going with a single recuperation voltage, typically maybe 35 kilovolt, then you see that still a lot of this energy is existing and goes to the collector. Now you will say, why are you not going to higher the recuperation voltages? But you have to select the recuperation voltage in a reasonable level. Otherwise, you get too much electrons going back to the cavity, which are just reflected by the recuperation voltage and going back to the cavity. So now think about, you take a two-stage collector. Then you see here that you have in the first stage something where you can have already significant energy saved, and the remaining you can save in the or recuperate in the second stage. So what you have to do for this, that you guide the electrons properly to the collector walls or the collector potentials. And secondly, also that you, because you have very high energies, that you are not getting secondary electrons going back to the cavity. And here you see the z-axis. So this is the direction of the electrons with different, take 3 electrons with different velocities. Then normally they will follow the magnetic field line and going in that direction. If we consider an electric field, now we have to see an electric field which is tangential to the velocity. So normally you will say how you can do it, and I will show you later how to do it. But from theory, if you do it, then you will give a so-called E cross B force. So this E cross B drift, which is then resulting from this, makes that the electrons in the different velocities will go to the different collector areas. So what you need is an electric field which is tangential to the axial, to the axis of your gyrotron, and you have to think about how you can realize it. And as such, you see here the concept of a multi-stage depressed collector, which has exactly this, achieves exactly this axial electric fields with electrodes, and you see here like a sawtooth, more or less, that it is cut and has a certain potential as such. In the first electrode, a recuperation voltage of 11 kilovolt, in the second 46 kilovolt. So here you, on the right-hand side, you find the construction of the first short pulse gyrotron, and you see this is a status which is already a bit outdated, but this is, we have more or less all the parts here and build it together, so that we build the very first short pulse collector. Yes, first without cooling on this, or with minor cooling already on this, so that we can show the principle of the collector. So this shows you that we are advancing quite fast towards multi-stage depressed collector systems for gyrotrons. The second is, of course, that we started together with Greifswald, so with IPP Greifswald, to use the gyrotrons, there's the W7X gyrotrons, to have smart control of gyrotrons. You will say, why? The issue is now that you want to have, of course, heating, but also plasma stabilization and diagnostics. For the very first, of course, you want to go for the output power. So you would like to drive your gyrotron at an area where you can get maximum output power. And when you remember the development in the car industry, so then you know from automobile, so from car, that before the year 2000, all cars did not have a lot of electronic systems in it. Then there was the famous worldwide known issue of Mercedes-Benz regarding its R-Class, this so-called ELK test. And every car got a so-called system in it that the car is kept in the stable state. So the ESP at that time, or you remember the ABS for the braking system of Bosch. Very similar you're doing here. You try to operate the gyrotron at an area where it is stable, or if you find that it has a dangerous situation, loses the mode, then you fastly go to a proper operation range again. And you have diagnostics, for example, the CDS diagnostics, where you want to have frequency stability, which you can achieve here on this. So that means you add new and improved applications with frequency stability, narrow spectral bands, and also controls for higher output power. So this means that the usual way just to optimize the physical design is not more sufficient. So you try to operate in, or try to add electronic systems to your gyrotrons. and then going to this advanced controls for higher output power, more accurate measurements, and new applications. And here you find something which has been done in a PhD of Fabian Wilde together with IPP in 2020, where he operated the W7X gyrotron in a very stable state and could get around 10% more output power in average out of a gyrotron, just operating at its absolutely limit before it loses the mode. So, and this, of course, if you have 7, 8, 9, or 10% efficiency increase, it sounds not much, but even for Greifswald, it is virtually one gyrotron more than 10 gyrotrons. When you look on the gyrotron itself and say, what can you do with frequency stabilization? This idea is also not very new, and frequency stabilization is done, and also in gyrotron, the principles of frequency stabilization is also very old, and I can say even in my PhD, I did something on injection locking of gyrotron. You can take the gyrotron as a voltage controlled oscillator, and more even, you can think about that the gyrotron is only a weakly non-linear oscillator. What does it mean? In zero order, so to say, a gyrotron is nothing else than a van der Pol oscillator. So you can derive and make equivalent equations for the gyrotron as van der Pol oscillators. With this, it means you know that every oscillator and van der Pol oscillator, is it an electronic system? It's a gyrotron. Or we did it also because students did not believe it, also with a magnetron, with a solid state oscillator, like Kurokawa tried it for radar applications or others. Or you do go even for mechanic systems is practically the same on this. So that means from the output, you bring in a signal into the gyrotron itself. And this is also something which you maybe remember that our colleagues of AIP in Russia, so Professor Denisov, others, himself is very much pushing for that. Of course, you need a second source, which is not this high power, and then you can stabilize the gyrotron and this. So what we need for that is that of course, if we do this injection locking, that of course we need to have something which is also feeding the field back into the gyrotron. As said also here, maybe as you consider it as a van der Pol oscillator, and if you're interested in injection locking or even chaos or others, this is maybe very helpful. But for injection locking, you can go maybe in 1946 publication of Adler about injection locking of oscillators on this, and you find that the gyrotron itself behaves exactly like this Adler equations, or better to say like Kurokawa, depending on how you look at the field and this, and then you find the things. So for the basic concept of the injection locking here on this, as said, you need, of course, not only an RF beam going out, you need also an RF beam going into the system. And therefore you have to build a certain launcher. And here you should look in that what our colleagues from Russia, this is a critical criteria. So as I said before, and also what I did theoretically from this is the one. The second is how you build a launcher system where you can have the two rotating modes going into the gyrotron. The one is more or less feed it into the gyrotron from the outside, reflected, and then interacting, and then making the injection locking in the gyrotron to stabilize the frequency. And this our Russian colleagues did, but also so Dr. Jin has done something and will present something also on the infrared conference, how to make the design on this system. So if you do it and you now treat this injected signal as some kind of say some injection in the standard oscillator. So A is the amplitude, say, for the mode which you have in the operating mode. F is the amplitude of the injected signal. K is the wave propagation number, so to say, on the mode on this. Then you find that you can calculate and can get the equations and the behavior. And as promised to you, what you see here, it's actually even to show that's very old. And I published these things in 1995 and 1996 already on the infrared conferences, that you find that the locking for a gyrotron is actually exactly the same in the first order approximation like a standard, like predicted by Adler. And the Adler curve is very simple. You only need the Q factor of the cavity. You need only the ratio of the injected power to the free running output power and get immediately your injection range. Not more you need. So if you consider the gyrotron instead as voltage controlled oscillator, say before also to say, why can we use this here and say, why is this interesting? It's frequency stabilization, but also what we've shown already. You can also lock to one mode and bring this mode to a certain area, which would not excite and would be a stable operation when you are without injection locking. So if you are taking now the gyrotron as voltage controlled oscillator, of course, what you can do is here that you consider that you have, of course, a cathode voltage. You have a body voltage for the W7X gyrotrons, which you use before for the depression voltages. And then you can, of course, shift the frequency of the gyrotron, knowing the ratio between the voltage and the frequency of the free running oscillation. With this, you can derive a control system, and that is done already. And that has been done also for operation in Greifswald for the tubes, tested for W7X and CPI gyrotron, which is also installed one there. And here you see this phase-locked loop system with an intermediate frequency of 45 megahertz to compare the free-running frequency and the loop or the reference frequency as such. And when we are doing this, we see here in orange the free-running frequency, and you see we are talking here about minus 1 megahertz to plus 1 megahertz. But you see here that we can even lock it exactly close to, much less than a megahertz. You can even go much, much lower down, and you see the side bands here, which you have, is something which we are at the moment improving, is showing something from the high voltage power supply, some 130 kilohertz variation in that is much depressed. And of course, this converts into the output frequency of the gyrotron. But you see, theoretically, you can exactly frequency lock the gyrotron. And this is, of course, for CTS diagnostics, for example, wonderful on this to make diagnostic and this, or later maybe make power combining, or later make ion cyclotron heating by having two tubes and doing exact difference frequencies for that. And then you can have maybe 30 megahertz difference frequency out of this gyrotron. So now to the last, coming to the Fulgor, having spoken a lot, coming to the Fulgor test stand. Yes, as I said, our old test stand, which was very successful, and you see it here, we have driven a lot of tubes. So the W7X, the ITER, and the W7X upgrade tube, the KRT 2 megawatt tube. But you see here, it's quite old, and as such, it is also, of course, consisting of an old linear regulators made of tetrodes on this, and also capacitor banks on this. Of course, if you look for modern test stands, you will never do it. And what we did is, of course, that we said we want to have a system where we can run really 10 megawatt input power, 4 megawatt output power. That means 2x2 beams on one gyrotron in some future, in maximum 3,600 seconds, and then with 50% duty cycle. Of course, theoretically, you can do it longer, but we limited it to have a limited heating of the transformers. You see it here, that are the so-called transformers coming from a 20 kilovolt line in and up converting to 90 kilovolts. And we have modulators on this, which are in series connected to each other. And this you can even regulate so that we can also operate multi-stage depressed collector operation on this. 80 modules on these things, and additional body modulator, so that we can run up to 130 kilovolt and up to 120 ampere on this for the future. Additionally, of course, it has a much more modern control room, everything digitized, everything with quasi-optical systems made. And we know that our industrial supplier is copying it, because this is also made for industrial testing here. So also this data acquisition, that you can really then give professional results to your customers if you have a gyrotron what you build. And of course, with a new microwave box, where you see in here the 2 megawatt load also waiting on this, and there's a quasi-optical line, of course, behind, which is made. And at that time we were waiting for the 10 Tesla magnet is the only what is not there. And here, this at the moment we have installed the W7X magnet for the 1.5 megawatt, which we will run. And this shall, by end of April, this system will come to normal operation then on this, and then we will use it together with the old test stand for testing. That you can see here regarding the system which is expected to go forward. With this, of course, I have no additional slides anymore. With this, I say thank you to all of the people who listened so long for this presentation. And I will end the presentation and come back to a visible state. And I hope some people are still listening. And yeah, if you have questions, I'm now open for questions.
Thank you very much, Professor Dr. Yellowneck, for nice presentations and very much information. Now I request the audience for invite questions and suggestions one by one. Please, it's open for questions.
I will say one line to Professor John Yellowneck, that everyone was listening till end.
Sorry?
Everyone was listening till end.
Okay, thank you very much. I was not sure, because I was not sure, is it now too deep or too soft? Of course, you are all experts.
No. I'd also like to say that it was very interesting, right from the, you started from the basics of the gyrotron and to the what level you have been doing. It's a very interesting, and because our interest is also because we have worked in the area of gyrotrons at Siri Pilani with the other institutions, including IPR. IPR was the agency which has been working with us, and 3 other agencies, IIT Roorkee, IIT VHU, and all, and Samir in Mumbai. So we tried to initiate this activity, though it was very late. It was we are unfortunate that we could start this activity very late, because it is a very costly affair. So naturally we need resources, but somehow we could develop and bring out a stage to the 42 gigahertz gyrotron with the help of IPR. They tested the gyrotron there. But now, of course, now the point is actually we have to work hard to take it further, so that we are able to develop this gyrotron at the required frequency and power level. That is what I would like to say. So that is a shortcoming. We feel that we are not able to do that. We are not getting the proper support from the agencies, so that we could take this work further. Otherwise, all these years what we have been doing, we just go on waste. So that's what though IPR is there, we have been working on that, they are developing the system, but basically they're taking the two gyrotrons from other sources and supplying, and of course they are making the system. But we are the one where we have to go ahead for developing the gyrotron of our own, with others, of course. That's what I feel, that we should somehow come forward, work together, that then they go to the government agencies or other agencies so that they can support and we get the support for developing the gyrotron of our own. But it was very interesting, and we have been already in contact with KIT for so long, so we know very well Doctor from and Officer Karthikeyan, of course, he is not there. He was with you for quite some time. And Professor Thum also visited and saw the gyrotron which was being developed at Sri Pilani. So it was very interesting, and it will be very beneficial for the youngsters who have been working in this area, particularly to them. Thank you very much.
I seek the permission of the chair, Dr. Lalit Kumar. May I seek the permission of the chair? Lalit Kumar, you are not audible. Dr. Lalit Kumar, not audible.
Please, Professor Basu, you don't have to ask permission. You
No, you are the chair.
Then I regret for not